Okay, so today we're going to take a look at changing volume and temperature. So let's make a couple of notes here. If we have a chemical reaction and everything is a gas, you can change the volume by compressing or decompressing it. So that means if you've got like the syringe that we were working with from Boyle's Law and you're adjusting the plunger, compressing it is going to make the volume smaller, and then decompressing it will make the volume larger. Agreed? Okay. And then if we're talking about a solution, so let's say we've got a salt dissolved in water, you can change the volume of a solution by evaporating the water or by adding water to it. So that means you would dilute it. So the volume would become larger when you dilute it because you're adding water to it, okay? And whenever we change the volume, aren't you also changing the pressure, because aren't pressure and volume inversely related? Because you learned about that in the gas chapter. So what's going to happen is the chemical reaction that's at equilibrium will shift when you make volume changes to relieve some of the added pressure, or they will replace some of the lost pressure. And we can actually predict which direction we will shift based upon the volume being increased or decreased. So let's make a couple of notes here. So let's write down that for volume increasing, okay, that means the pressure decreases. So then you would shift to the side with more particles to help restore the pressure. And that would help get us back to equilibrium. You're going to want to memorize this because this is the guide to actually completing the problems. Okay? And then there is one more scenario, and that's decreasing the volume. So let's write that down here. If I decrease the volume, that means the pressure will increase. So that means we should move to the side. I'll get it. We should move to the side with fewer particles. To help reduce that added pressure, and that will help us get back to equilibrium. So these two things will get you through the volume changes at equilibrium. And let's take a look at the top of the next page when you're ready. At the top of the next page, they gave us a reaction. And what I need you to get into the habit of is counting the coefficients that you have. So what I'm going to do first is I'm going to highlight the states of matter just to emphasize the fact that this is a gaseous reaction mixture. It's at equilibrium because it has the double arrows. And then you'll notice that you've got coefficients in front of the H2 and the F2. They're ones, right? Add them together. And then that shows you that you have two gases on the reactant side. On the product side, I have a 2 in front of HF. So that means I also have two gases on the product side. When the number of particles is the same, that means if you change the volume, you actually won't observe any sort of like response, okay? So here it says this equilibrium doesn't respond to a volume change. And that's because if I shift to the right or the left, since I have the same particles, I can't change the pressure. Okay, so because of the same number of gas particles on each side of the equation, there would be no observable change. Okay, so we have 2 gases on the left and 2 gases on the right. Therefore, there's no response. Does that make sense? Okay. In the examples that we're going to look at next, the number of particles will be different. Okay, so let's take a look at the sample problem that's in the middle of the page. Okay, in the middle of the page, you've got a reaction. Let me make this a little bit smaller. And it says that we are going to compress it. Okay, so when I compress a reaction mixture, you'll notice that these are all gases. Am I making the volume larger or smaller? Right, so the volume is decreasing. What does that do to the pressure? Yeah, so that increases the pressure. All right, so let's count how many gas particles we have on each side. I have 2 gas particles on the reactant side, and I have 1 gas particle on the product side. Okay, so since the volume decreased and the pressure went up, I need to relieve that added pressure. So that means I need to shift to the side with fewer particles. Which would that be? The right side. So we're going to shift to the right. The reason we shift to the right is to reduce the pressure. Does that make sense? Okay, because if I have fewer particles, there are fewer particles colliding with the surface of the container, and that's what causes pressure. Okay, let's go to the next page. At the top of the next page is a sample problem with a solution. So this was a gaseous mixture, and then at the top of the next page, this is a solution. You'll notice that everything is dissolved in water. And we are going to dilute it. So when you dilute a solution, you add water. So that means the volume is increasing. What does that do to the pressure? Yeah, so the pressure is going to decrease. Okay, we need to bring the pressure back up to help us get to equilibrium. So let's count how many particles we have on each side. I have 2 ions on the reactant side, and then I have 1 particle on the product side. So since the pressure dropped, I need to move to the side with more particles. Which side would that be? The left, right. So we will shift to the left. And the reason we shift to the left is because there's more particles. They will collide with the surface of their container more often. That will result in the pressure coming up, and that will help get us back to equilibrium. Yeah.
What's the difference between like the ions and
Ions just have charges on them. That's all. They're still particles. They're just ion specific. Does that make sense?
Yeah.
Okay. All right, let's go to the practice problems. I want you to do the practice problems with the person sitting next to you, and let's see what you come up with. Okay, when you compress something, are you increasing or decreasing volume? Okay, so that means the pressure went up. All right, so if you take a look at the particles, you have 2 gases on the left, and you have 3 gases on the right. So if we're trying to relieve this extra pressure, we would need to shift to the side with less. So you want to shift left. Okay, because that will bring the pressure down. Does that make sense? Okay. The system below is diluted. So does that mean I increased or decreased the volume? Increase volume, which decreases pressure. Okay, so now let's look at the number of particles that we have. You have 1 ion on the left-hand side, and then you've got 3 ions on the product side. So if the pressure dropped, I need to bring it back somehow. So you want to shift to the side with more particles. So you're going to shift to the right, and this will bring the osmotic pressure up. So the pressure when we're dealing with solutions is called osmotic pressure. You probably heard about that in biology. Okay. Number 3. All right, the volume is decreased. Okay. Will the equilibrium system respond? Well, let's see. We've got 2 gases on the reactant side and 2 gases on the product side. Anything going to happen? No, nothing will be observed because we can't shift to one side or the other because we have the same number of particles on each side. Okay, I can't relieve anything. Okay, we good with this? Let's go to the next page. Okay. Now we're going to talk about temperature changes. And what I'm going to do is I need to give you a couple notes on temperature changes before we proceed. So let's make a note that if it is an endothermic reaction, which is a positive delta H, if you add heat, you will shift to the right. If you remove heat, then you will shift to the left. And this you should absolutely memorize. This will get you through half of it. Then we need to talk about exothermic reactions. So why don't I write exothermic reactions over here? Exothermic reactions have a negative delta H. So if you add heat, it will shift left. And then if you remove heat, it will shift to the right. Again, memorize this. Okay, let's take a look at a sample problem. Here they've heated something, okay? Anytime they change the temperature, you absolutely need to first figure out if it's endothermic or exothermic because that's going to determine which side you shift to. Notice they gave you a delta H value after the equation. It's positive, so that means this would be endothermic, okay? That means heat is a reactant, okay? This will help you figure out, if you don't memorize, which side to shift to, okay? So if I heat something, aren't I adding more of a reactant if it's endothermic? Does that make sense? So when you add more reactant, don't you always move to the other side? So we are shifting right because we've got to bring this heat down. So we're going to consume some of that added heat when we shift to the right, okay? Now, when you change the temperature on things, we're going to be dealing with changing kinetic energy and potential energy. So heat makes things move. So that means we have added kinetic energy because everything's moving more. And by shifting right, we're converting it into potential energy, which is now stored, and that helps me get back to equilibrium, okay? All right, turn to the next page when you're ready.